Pick any map. Color it so neighboring regions differ. 5 colors are always enough. No matter how twisted, no matter how many regions, 5 does the job. By the end of this video, we will see exactly why. Forget the colors for a moment and look at the bones of a map. Every map gives you a graph. Each region becomes a dot, and each shared border becomes a line connecting 2 dots. The graphs you get this way have a special property. You can draw them flat on a sheet of paper, with no 2 lines crossing. We call those planar. Most graphs are not planar. Take 5 dots and connect every pair. That is K5. Try to redraw it without crossings. Move the dots anywhere you like. Bend the lines however you want. 2 lines will always cross. K5 cannot be flattened, but every map can. So when we say 5 colors are enough for any map, what we really mean is 5 colors are enough for any planar graph. A coloring is simple. Paint each dot a color. The only rule, if 2 dots are connected, they have to wear different colors. Some graphs need only 2 colors, some need 3, like a triangle. The question for us is the smallest number that works for every planar graph, and that number is 5. Planar graphs hide a numerical relationship. Count 3 things: the dots V, the lines E, and the empty regions the lines carve out F, counting the unbounded outside as 1. For any connected planar graph, V minus E plus F equals exactly 2. That's Euler's formula. Now the lever. Each region is bounded by at least 3 lines. Each line is bounded by exactly 2 regions. So if you count line region incidences, you get 2E from one side and at least 3F from the other. 2E is at least 3F. Plug that back into Euler's formula. V minus E plus 2/3 E is at least 2. Simplify. E is at most 3V minus 6. We just bounded the edges. Now turn that bound into a fact about the dots. The degree of a dot is how many lines touch it. If you add up degrees across every dot, every line gets counted twice, once for each endpoint, so the sum of degrees equals 2E. And since E is at most 3V minus 6, the sum of degrees is at most 6V minus 12. The average degree then is less than 6. If the average is less than 6, at least one dot has degree 5 or smaller. Always. Every planar graph has a vertex with at most 5 neighbors. We can use this fact. We can find a vertex with degree at most 5. Pick it and call it V. Remove V from the graph. What's left is still planar, just smaller. Imagine we already know how to 5-color any smaller planar graph. Color it. Now bring V back. Its neighbors are already colored. The question is, can we always pick a color for V that does not clash with any neighbor? If fewer than 5 distinct colors appear among V's neighbors, we just pick a free one. The interesting case is exactly this. V has degree 5, and the 5 neighbors wear 5 different colors. Kempe's idea. Look at V1 and V3, color 1 and color 3. Trace the longest possible path away from V1 that uses only colors 1 and 3, alternating. Call that the 1,3 Kempe component of V1. In this case, the chain stops before reaching V3. V3 is not in V1's component. Swap colors 1 and 3 throughout the chain. This still gives a valid coloring. Any vertex outside the chain that touches a chain vertex has a color other than 1 or 3 by the very definition of the chain. So nothing clashes. But now the neighbors of V wear colors 3, 2, 3, 4, 5. Color 1 is free. V takes color 1. But sometimes the 1,3 chain from V1 runs all the way to V3. That is the second case. Combined with V itself, this chain closes into a cycle in the plane. And here planarity bites. The cycle splits the plane into an inside and an outside. V2 sits inside, V4 sits outside. Now look at V2's 2,4 chain. To reach V4, it would have to cross the cycle, but the cycle is built from colors 1 and 3. The 2,4 chain is built from colors 2 and 4. They share no vertices. The chain is trapped on its side. So the 2-4 chain starting from V2 does not reach V4. Swap colors 2 and 4 along it. V4 stays untouched. V2 becomes color 4. The neighbors of V where 1, 4, 3, 4, 5. Color 2 is free. V takes color 2. The proof is finished. 2 ideas got us through. Euler's formula forced some vertex to have at most 5 neighbors. Kempe's chain swap handled the hardest configuration, so 5 colors are always enough for any planar graph. The same trick almost works for 4 colors, almost, but that's another story.